This video will review some of the concepts we've seen recently involving vector-valued functions. We have a vector-valued function r. That's just a function that takes a parameter t and gives you a vector in R3. That vector-valued function might be parameterized by arc length, meaning the curve that it traces out in space could be traversed with unit speed at a constant speed of as you go along the curve. The unit tangent vector t is defined to be the derivative of your vector-valued function divided by the length of that derivative. That makes it a unit tangent vector. If you happen to be parameterized by arc length, then the formula is a bit simpler. This speed is just 1. The unit normal vector, that's the second derivative. That's the derivative of the unit tangent vector, t prime, divided by the length of t prime, making it a unit normal vector. If you happen to be parameterized by arc length, then doing that operation on this vector gives you the second derivative divided by the magnitude of the second derivative. The unit binormal vector, that's defined to be t cross n. If you happen to be parameterized by arc length, then that also could be written as the cross product of these two vectors, r prime cross r double prime, divided by the length of r double prime. Curvature. Curvature kappa. That tells you how curvy your curve curves. If your vector is not parameterized by arc length, then you could find curvature by looking at the magnitude of the derivative of the unit tangent vector and dividing by the speed length of r prime. An alternative way to find curvature is by doing this cross product calculation, r prime cross r double prime, divided by the magnitude of r prime cubed. If r happens to be parameterized by arc length, then this is a little bit simpler because the magnitude of the derivative of r is 1, meaning that the curvature is simply the magnitude of t prime. But in that case, since t, if parameterized by arc length, is simply r prime, this is the magnitude of the second derivative of your vector-valued function r. Okay, velocity. Velocity is the derivative of your vector-valued function, and there's no simpler expression if you happen to be parameterized by arc length. Speed is the magnitude of the velocity, and if you happen to be parameterized by arc length, the speed is always 1. And acceleration, that's the second derivative of your vector-valued function. No simpler expression when you're parameterized by arc length, but I will say that acceleration can be expressed as a linear combination, as a combination of the unit tangent and the unit normal vectors. You do not need a unit binormal vector at any point in calculating acceleration, so this would be the derivative of the speed times the unit tangent vector. So this is not a vector. This is a scalar, like a constant function. T is a vector, so you're getting a scalar times a vector, plus the speed squared times the curvature. This is another scalar function, times the unit normal vector n. So these are the concepts we've seen most recently in our course. Excellent.